Now we're going to revisit induction and kind of solidify the process that we worked our way up to in the last video. So we're going to formalize the process of proof by induction. So we're going to look at some of the computations from the in-class activity. We're going to note how each step that we complete is used for the next step, and that is the fundamental process of how induction works. And then we're going to describe the formal process of induction about how we're going to actually prove the formula that we looked at in that activity. And finally, we're going to prove the result from the in-class activity using proof by induction. Alright, so remember that our goal was to prove a formula for cosine theta plus I sine theta all to the nth power. And remember, I is our old friend square root of -1. So we're going to start with n equals 1. And that one's pretty easy. We're going to figure out that one just whatever way we can. So we look at cosine theta plus I times sine theta to the 1 power. And that, well, anything to the 1 power is itself. And so we get cosine theta plus I sine theta. That looks like a pretty good formula to me. Now for n equals 2, we're going to square that. And we just go through the normal process that we do for squaring. We square the cosine, we square the I times sine, and remember, when we square that I times sine, I squared is -1, so that's going to give us minus sine squared theta. And then when we do our outer and inner product, we're going to end up with I times the quantity 2 sine theta cosine theta. And then we're going to collect the real parts together and the imaginary parts together and get cosine squared theta minus sine squared theta plus I times 2 sine theta cosine theta. And the one thing I hope you noticed is on the left hand side we have exactly the formula for cosine of 2 theta. And very interestingly, on the right hand side behind the I, we have exactly the formula for sine of 2 theta. So we get a fairly nice formula, cosine 2 theta plus I sine 2 theta. So off we go to n equals 3. We have, well, now we got to cube that. Now if we want to go through the process that we did before by like cubing everything out and seeing what we get, I will tell you right now you can try that, but it's going to be a bloody mess. So what we're going to try to do is piggyback on the work that we just did to find the formula for n equals 3. And so what we're going to do is, remember, cubing anything is squaring it and then multiplying it by it again, right? So we could think of cosine theta plus I sine theta cubed as cosine theta plus I sine theta squared times cosine theta plus I times sine theta. And the advantage of looking at it this way is we already have a really nice formula for cosine theta plus I sine theta squared. We just proved it. In fact, we just proved that it was cosine of 2 theta plus I times sine of 2 theta, and then we're just going to multiply that by cosine theta plus I times sine theta. And the nice thing about writing it this way is when we FOIL this, it's actually not going to be too bad, right? So when we multiply, we're going to multiply cosine 2 theta times cosine theta. We're going to multiply cosine 2 theta times I sine theta, that's the second term. Then we're going to multiply I times sine of 2 theta times cosine theta, that's the third term. And then when we multiply I sine 2 theta times I sine 2 theta, or I sine theta, remember, multiplying the i's together gives us -1, and we just end up with minus sine 2 theta times sine theta. Once again, we collect all the real terms together and all the imaginary terms together. And oddly enough, for the real part, that looks a lot like the sum of angles formula for cosine, where the angles are 2 theta and theta that we're adding together. Right? So if we look at what the formula for cosine of 2 theta plus theta is and split it up, we get exactly cosine 2 theta times cosine theta minus sine 2 theta times sine theta. So that works out nicely. And if we look at what's multiplied by the I, that is exactly the formula for the sum of angles for sine, where the two angles are, again, 2 theta and theta. And when we simplify those, amazingly, it comes out to cosine of 3 theta plus I times sine of 3 theta. And we can continue this process as long as we want. If we want to find a formula for n equals 4, we're going to take cosine theta plus I sine theta to the 4th power. We're going to split that up into cosine theta plus I sine theta to the 3rd power times cosine theta plus I sine theta. We just proved a nice formula, coincidentally, for cosine theta plus I sine theta to the 3rd power. That is cosine of 3 theta plus I sine of 3 theta. Now we can FOIL out what remains. We can collect the real terms and the imaginary terms. And then again, we note that the real part is the formula for cosine of the sum of angles 3 theta and theta. And the imaginary part gives us I times the sine of the sum of angles 3 theta plus theta. And we end up with cosine of 4 theta plus I times sine of 4 theta. If we want to get the formula for n equals 5, we have, well, we're going to do the exact same thing. Hopefully you're already bored, right? Because that means we're ready to actually do some real proving. But we're going to split it up into taking it to the 4th power times whatever the quantity is to the 1st power. We're going to use the formula we just proved for cosine theta plus I sine theta to the 4th power. We're going to FOIL it out. We're going to collect like terms, or collect the real terms together and the imaginary terms together. We're no longer surprised that we end up with the sum of angles formula for cosine and for sine. And then we end up with cosine of 5 theta plus I times sine of 5 theta. And I want to emphasize so much that every time we get our new formula, we use the formula we just proved, first of all. And second of all, the process that we go from going from one step to the next step is pretty much exactly the same. So we should be able to mechanize this so that we can always go from any step to the next step. All right, so patterns, you probably figured out all these by yourself. First of all, it looks like the formula that we're going to end up with is cosine theta plus I sine theta to the n power is equal to cosine of n theta plus I times sine of n theta, right? Each of those cases, that's exactly what we got. There's no reason to think that the formula isn't going to keep going. Every time we proved one case of the theorem, we used the result from the case that we had just proved from the previous case. That's important. And each case we proved was pretty much proved the exact same way. We just used slightly different numbers. When we go to 3 to 4, it's 4 to 5 is the exact same, except instead of 3 we put 4, instead of 4 we put 5. And what this suggests is, in order to prove, all we really need to do is prove the following. We need to prove the case for n equals 1, which we actually did at the very beginning. And we need to show that whatever the formula we just proved, say at n equals k, can always get us the right formula for the next case. That would be n equals k plus 1. So here's our theorem, and we're going to dig into the formal proof by induction. So our theorem, of course, is for all integers n, we have, actually it should be all natural numbers n, oopsies, that's a little typo. We have cosine of theta plus I times sine theta to the nth power is equal to cosine of n theta plus I times sine of n theta. Alright, here's our proof. We begin with n equals 1. We have cosine of theta plus I times sine of theta to the 1 power equals cosine theta plus I times sine theta, and that is exactly the same as we know that cosine of 1 times theta is equal to cosine of theta, sine of 1 times theta is equal to sine theta. Thus, cosine of theta plus I times sine theta to the 1 power is equal to cosine of 1 times theta plus I times sine of 1 times theta. So, the formula works for n equals 1. Now we need to show how to go from the n equals k case to the n equals k plus 1 case. And look at what we do here. By go from n equals k, what we really mean is that we're assuming that the n equals k case is true, that we just proved it, that it works out just fine. In other words, we're assuming that cosine of theta plus I times sine theta to the k is equal to cosine of k theta plus I times sine of k theta. By 2n equals k plus 1, it means we have to show that the n equals k plus 1 case is true. In other words, we're going to show that cosine theta plus I times sine theta to the k plus 1 power is equal to cosine of k plus 1 times theta plus I times sine of k plus 1 times theta. And the computations that we're going to use are not going to be at all a surprise to you. You've seen them before. They're just going to have some k's in there. So we want to find out what cosine of theta plus I times sine theta to the k plus 1 is. We're going to split it into cosine of theta plus I times sine theta to the k times cosine theta plus I sine theta. We are assuming that cosine of theta plus I times sine theta to the k is equal to cosine k theta plus I times sine k theta, so we can substitute that in. Now we do the foiling just like we did before. We collect the real terms together. We collect the imaginary terms together and factor out that I. That top formula is exactly the formula for the sum of angles formula for cosine. That gives us k theta plus theta. And what is multiplied by I is exactly the formula for the sum of angles formula for sine of theta, where the two angles are k theta and theta as well. All right, so that's what we have so far. Now, k theta plus theta is the same as k plus 1 times theta, so we can substitute that in. And it just so happens that's exactly the formula that we were trying to prove. That's the formula for the k plus 1 case. And that completes our proof. So, just to summarize, proof by induction is for proving theorems that look like, well, they look like something like for all n greater than or equal to 1, p of n, where here p of n is some open sentence, which means that it's a sentence that becomes a statement when you put in a number, a natural number for n. And here are the steps you use in proving that theorem, that general form of the theorem, by induction. First of all, you prove what is called the basis step, or the base case, which means you're going to prove the theorem for the case that n is equal to 1. Right? So, in other words, you're trying to prove p of 1. Then your inductive step, you assume that the theorem is true for n equals k, right? In other words, assume p of k. And what you're really doing is you're thinking that p of k, that n equals k case, is the one that you just proved, so that you assume it. And then you're going to prove the theorem is true for n equals k plus 1. N equals k plus 1 is the case that you want to prove next. That's your next step. You're using the previous step that you just proved to prove the next step that you want to prove. And again, that's the same as proving p of k plus 1. All right, so now I think you're ready to work on some induction proofs. The name of the PDF file is Proof by Induction, and see what you can get.